Hi guys, so today we're going to look at how to find an inverse of a function. Inverses are something that they're going to keep coming back up throughout the year. We'll spend a lot more time with them and a couple of the other functions, but it's important for us to have an understanding of what an inverse is. Now you actually have seen an inverse before, and you saw it in geometry. So if you remember back when you were doing trig, and let's say you had a triangle like this, and you had to find what that angle was. So if you remember, you had to do sine theta, that'd be tan theta is opposite over adjacent. In order to find that angle, what you had to do was you had to use tan inverse of 2/3 on your calculator. So that little tan to the -1, that was the inverse of tangent. So it was a different operation. Instead of actually finding using the angle, we were trying to find what the angle was. So that was your first experience probably with an inverse. So an inverse, very similar, it's going to be the opposite operation. So this gives us an equation. It says f of x is equal to 2x plus 4. So the inverse is going to be basically what happens when we switch x and y. So what I'm going to do is I'm going to flip my x and y. I'm going to solve for y, so I'm going to divide by 2. So I get that y equals 1/2 x minus 2. Now the notation that we're going to use is this very similar to what you used for sine inverse and cosine inverse, that f to the little -1. So f inverse of x would be 1/2 x minus 2. So all we do is we flip our x and our y's. Now what's important to know about this, an inverse is different than a reciprocal, and this will come up especially a lot next year. So an inverse is not the same thing as a reciprocal. A reciprocal is like when we had 1/2 and we flipped it and the reciprocal was 2. Those are not inverses of each other, okay? All right, so let's go ahead and look and see what these graphs look like. So I'm going to go ahead and graph the inverse. So that had a y-intercept of -2 and a slope of 1/2, so up 1 over 2, up 1 over 2. So that is my inverse graph. Then my other graph, my original, 2x plus 4, so slope of 4, y-intercept of 4, slope of 2. And you'll notice both of those go through the same point. Now, they don't have to, but in this case, they both do. So what's happening here, these graphs are basically reflected over the line y equals x. So if I were to draw the line y equals x, those graphs would be flipped over that line. Our inverses will be. Another thing you'll know is we talked about how we switch the x and the y in order to find the equation. Well, that's what's happening on the graph as well. So this point over here, that point was -2, 0. Well, if you flip the x and the y, then you get 0, -2. This point up here was 1, 6. So on the inverse, that point is 6, 1. The reason both of these graphs are going through the point -4, -4 is because they have the same x and y value. So if I flip the x and the y, it's still -4, -4. So that's how I would find the inverse off of a graph, which is what we'll do here. But basically, what's the most important thing to understand about inverses, we're switching our x and y's to find our inverses. All right, now, where this ties back with composition is something we're going to look at in a second because I skipped a slide. So we're going to get some more practice on the graphs here with inverses. All right, so on this first one, it gives us a graph, and we want to sketch what the inverse looks like. All right, so in order to do that, we're just going to flip our x and y points. So the first point on here is -3, 0. So the inverse function then would go through 0, -3. Next point on here was 0, 3. So the inverse would go through 3, 0. And then if I took 3, 0 from the original graph, and I flipped my x and the y, that would go through 0, 3. So that is my inverse. So the first question is whether or not that is a function. So that is not a function because it does not pass that vertical line test. So if you remember back from Algebra 1, a function every x has to have exactly one y, and that is not the case here. All right, so now let's look at domain and range. So the domain of the original, the farthest left was -3, and it did touch it. The farthest right was +3, and it did touch it, and we just used brackets. The range of that function The lowest y value there on the original was 0. The highest y value was 3. So my range was from 0 to 3. All right, now we're going to write the domain and the range of the inverse. So the domain, the farthest left was 0. Farthest right was 3. Then the range, the lowest point at the bottom was -3, and the highest point was 3. So if you notice on here, look what's happening with your domain and your range. And if you think about it, it makes sense. Domain is the x's, and if we're flipping the x's and y's to find the inverse, well then the domain becomes the range. Same thing the other way. The range and the domain are flipped basically between the inverse and the original function. And that's going to be important later on when we start looking at inverses for our square root and quadratics. All right, so go ahead, pause the video, try the next one, find the inverse by flipping the x and y's. All right, so on this graph, it goes through 0, 5. So 5, 0 will be the next point. Original went through 1, 4, so this one's going to go through 4, 1. The original went through 4, 3, so this is going to go through 3, 4. And then the original also goes through 9, 2, so we're going to go through 2, 9. And then the original didn't have an arrow, but I'm going to go ahead and put an arrow on it. So the purple graph is my inverse. In this case, yes, the inverse is a function. It passes that vertical line test. Every x has exactly 1 y. So now let's write the domain of the original, the one in black. So the farthest left of the original was 0, and then it kept going to infinity. Range, bottom to top. The lowest y value there is -infinity because that arrow keeps going down. The highest y value up there would be 5. Then knowing what we know these two will flip, but let's go ahead and just look at the graph to double check. So the domain of the inverse, it keeps going to the left, so -infinity, and then the farthest right has an x coordinate of 5. It touches it, so it's a bracket. Lowest point on the inverse is 0, and then it keeps going up to infinity. All right, so now we're going to look at how this relates with composition. So composition can actually be used to prove whether or not two functions are inverses. So the way we would know that it's inverses by composition, we're going to do f of g of x, then we're also going to do g of f of x. And if both of those answers simplify all the way to just x, then those functions are inverses of each other. So let's go ahead and try this one. So f of g of x. So g of x is 1/3 x plus 1/3. So every x in the f of x function is going to get replaced with that value. So 3 times 1/3 x plus 1/3, 3 times 1/3, and I forgot my minus 1. So 3 times 1/3 is x. 3 times 1/3 is 1. The 1 minus 1 cancels out. I'm left with just x. So now we have to try the opposite way. We have to do g of f of x. So we're doing g of 3x minus 1. So in that function, the x gets replaced with 3x minus 1. I can distribute. My 1/3 cancel out, and I'm left with just x. So since f of g of x was x, and g of f of x was also x, those two functions are both inverses. All right, so very similar to what we did with composition, we're going to look at inverses from both a table and a graph as well. So from looking at the table, f of x and g of x will be inverses if the x and y's are flipped for every single point. So -2, -2, x and y flip. -1, 1, x and y flip. And if you notice, on every one of those, the x and the y values have flipped. So f of x and g of x in that first table, yes, are inverses. But if you look at B, the x and y values have not actually changed places. All that's happened is they've been made negative. That is not an inverse. So we have to actually switch the x and the y's. We can't just try and make one negative. All right, and the last thing we're going to look at is mapping. So you may not have seen this since Algebra 1, but mapping just shows what the x's are, what the y's are, and it draws those arrows to show which y's go with it. So the first one, the input is our x's, the output is our y's, and it's showing you what each x goes with. So this mapping is just telling you that -4 and -2 is a point, 0, -3 is a point, 1, 2 is a point, and 4, 2 is a point. So that's how we would read that. So to find my inverse, I just have to switch x and y's. So the input becomes the output, and then they still match up the same way. So -2 still goes with 4, -3 goes with 0, 2 goes with 1, and 2 goes with 4. So the points on this inverse, again, it would just be the x and y's flipped. But if you notice now, the inverse is not a function because, again, every x has to have exactly one y, and on this inverse now, the x value of 2 has 2 y's that go with it. So the inverse is not a function. But again, we just find that inverse by flipping x and y's. All right, so that is it for inverses. So we're going to look in class, we're going to review composition and operations and inverses, and we'll look at a little bit harder examples with a little bit more difficult algebra, but the core concept really is just this right here. To find an inverse, we're just going to switch our x and our y's.